So why are we interested in gravitational lensing? What do astronomers want to do with gravitational lensing? In 1919, it was just used to verify Einstein's theory, but now astronomers use it as a tool in their toolkit to study the universe. So I've introduced multiple image sources. Those are very important because they tell us how dark matter in the universe is clustered on fine scales. Now, you probably know that the universe contains a large amount of dark matter, and we want to know how does it interact with normal matter, the stuff that makes up you and me. How is it clustered? What kind of properties does it have? Is it cold dark matter so that it doesn't interact with anything? Or is it slightly warm, which means it might interact with normal material? And we use what we call multiple images. This is sometimes in the business called strong lensing, because you need a very strong gravitational field to induce multiple images. But weak lensing is another technique which maps the distribution of dark matter on much larger scales. So this is telling us about cosmology on the very largest scales. And then finally, we use gravitational lensing as sort of telephoto lenses that we attach to our telescopes to make them more powerful so that we can see distant objects more easily than we would otherwise be able to do. So I'll just show a few illustrations of these three techniques. So I introduced this cluster where all of these multiple images have been charted in great detail, and what you see shown as contours is the mass that is required to produce the location and the shape and the orientation of each of these multiple images. And so when we do this, we find that there's 50 to 100 times more mass in this area in the lens than can be accounted for by the stars in the galaxies themselves. So just to remind you, all of these little letters are background objects that are imaged. So there's A1, A2, and A3 are multiple images of a background object. Q1, Q3, and Q2 is another. So each of these multiple images is like gives us a ray tracing through this gravitational field that allows us to chart how the mass is arranged in this cluster. And you can see it's centrally concentrated. We can go one step further and do this for many clusters and look at how the mass is, how the density of dark matter falls off away from the center of the cluster. And we can compare this with numerical simulations that account for the nature of dark matter, whether it's completely cold or slightly interactive. Now, weak lensing is quite remarkable because when we look at the sky away from any lens at all, just looking at the sky directly, it's slightly distorted by all the dark matter that lies between us and the faint objects. So this is a sort of artist's illustration of the light from a distant object constantly being deflected by small amounts of dark matter as it makes its way to through the universe. And you might think it's impossible to measure this effect. It was first detected in 2000 by a number of groups, and we call this weak lensing. And the trick is that you're looking at these background objects through a whole array of dark matter that's distributed through the universe. So in an idealized situation, all of these background galaxies would be these little points of light, and each one of them would be very slightly distorted by the dark matter. And so the trick is, of course, to observe this distortion pattern and convert it into a map of the dark matter. And this is probably the best map that we currently have. It's an analysis done with the Hubble Space Telescope. And what you're seeing here is a map of the dark matter in blue of a very small area of sky compared to a map of the stars and galaxies on the left. And although there are some differences, like down here, for instance, broadly speaking, you can see that the dark matter is not independent of the galaxies. It's actually providing the scaffolding. The dark matter is providing the basis for the growth of galaxies and starlight. And there's a lot more dark matter in terms of kilograms per unit volume compared to normal stuff that makes up stars and galaxies. So this is probably the best dark matter map that we have. So the final application is this use of a cosmic lens to provide a boost to the power of our telescopes. So as we look deep in the universe, we're looking back in time. And of course, one of the exciting areas of research now is to study the very earliest objects seen when the universe was very young. Now, that's very difficult because the distant objects are, of course, extremely faint. But if we look through a cluster of galaxies, we can magnify these distant objects by factors of 10 or 20 or so. And so here is a list of the most distant galaxies that have been found over the years with the use of gravitational lensing. And one of the most distant galaxies that we currently know has been found by this technique. So the idea is that the magnification of this foreground cluster is a strong function of position in the cluster, and this red line is what we call the critical area where the magnification is highest. So that's where one would expect to see multiple images of objects seen when the universe was very young. Now, of course, if you enlarge a galaxy, when you magnify it, you can actually enlarge it on the sky, so it also acts as a magnifying glass for enlarging the object in its angular size, and that means that you can look at the internal properties of distant galaxies. For example, you can look at whether they're rotating and whether they have, whether their chemical composition changes across them. And so a number of these objects have now been studied. So these are distorted galaxies at high redshift for which one can measure their angular rotation, whether they're spinning. And this, of course, tells us how galaxies evolve in great detail. So I think it's definitely an amazing technique. It was never thought by Einstein to be much use when he discovered it. But as you can see, it's a very valuable probe of dark matter. It enables us to explore the distant universe, and there are many other things that it can be used for. So Einstein, I think, would be very impressed with the progress that's been made in gravitational lensing.